theme running through it. And to open, I'd like to invite Jane Wheelwright to talk on new ways to bring together drilling and subsurface data. She's going to introduce herself because I don't have her bio.
Sorry, Hamish. Good afternoon. My name's Jane Wheelwright and I work for Dynamic Graphics. For those of you unfamiliar with the company, Dynamic Graphics is a software development company specializing in the earth science arena and specifically in geologic modeling, well planning and 4D co-visualization. I'm very pleased to be speaking at this collaboration conference. It's a topic very dear to my heart and one that I spend a lot of time trying to persuade people to follow up as well. I'm just hoping that having the first slot after lunch that no members of the audience will drop off at the back. As a company, I think Dynamic Graphics is quite innovative. We tend to sort of see ahead in terms of what is going to be coming in terms of the industry. And we recognized several years ago the value of collaboration between different disciplines and the importance of being able to co-visualize data from a variety of sources, cross-discipline, cross-platforms, and cross-location. At the time, PowerPoint was pretty much the cutting edge of data integration. No offense to Paul, but it wasn't the ideal way of bringing data together from different sources. And we actually found it quite a challenge to persuade the industry that there were very real benefits in bringing data together. At the time, I think the general opinion was that if data could be viewed and analyzed successfully in its own native package, why was there any benefit or any requirement to take a holistic view and look at other data in conjunction with their own data? In recent years, however, there has been an increased awareness of the powerful benefits in areas such as reservoir management and decision making. Actually taking a collaborative viewpoint of data actually reaps very, very sizable rewards. And the work done to encourage data standardization by companies such as Energistics, promotion of the concept by individuals such as Dave Bamford, I don't know if Dave's here today, and the willingness to engage in systems whereby collaboration can become a reality by companies, I hate to mention BP again, but companies such as BP, that has brought about a sea change in perception. And I do find now that there is a much more of a willingness to engage in terms of looking at collaborative solutions to data management. The benefits speak for themselves. Using all the information available at your disposal highlights any concurrence, any inconsistency, saves time, and ultimately leads to the best possible decision making. Dave Bamford mentioned in one of his blogs that we'll never be able to actually see our reservoirs. You can't peel back the earth and look at the reservoirs. You can't, in fact, ever truly visualize them. So it's imperative that we can see and use all the data that we do have available. And I think there has definitely been a move towards actually incorporating data together. The reality of working collaboratively with data is still, however, an exception. There are very few cases where I'm going around oil companies where you actually see a true collaborative approach, and there's a lot that can be done. I'd like to move on from this morning's session, which was more looking at system architecture and the way to bring companies together and look at more specific issues, and in particular the union of well data and subsurface data. So what I'd like to show is collaboration between the drilling and subsurface arenas using a well planning and directional drilling package in a co-visualized vendor-neutral environment. And these particular areas are traditionally ones that do not communicate at all. Data is normally sent iteratively back and forth between the groups, which can take days, weeks, months. I mean, it can take years to plan a well working on a system like that. We've piloted a study using this new integrated approach, and the conservative estimates coming back from users is that it can save up to 90% of the time traditionally spent, and also gives far more confidence in well positioning in terms of both hitting targets and collision avoidance. I was pleased to see actually Landmark, Ewan's giving a talk later which is looking at some of the financial implications as well, and it's nice to see that we're not a lone voice in the wilderness, that there is now this consensus towards taking an integrated approach. So the software packages we're going to look at today are both developed by Dynamic Graphics. We're going to look at Well Architect, which is an advanced well planning and directional drilling package developed in conjunction with Baker. So it's Baker's directional drilling package. So it contains all the necessary requirements for a drilling package, including all the anti-collision avoidance algorithms. And in conjunction with Well Architect, we're going to look at COVIS 4D, which is a vendor-neutral environment. And the big important thing here is that data can be brought from a myriad of different software packages into the same area. So it avoids the PowerPoint route. And what this gives together is a very efficient, effective well planning, drilling and survey management tool. So how we can look at well planning in a traditional sense is really looking at it in terms of a brick wall. You have the drilling on one side, where you have targets that have been sent from the subsurface arena, and what the drillers do with this is they plan a drillable trajectory based on J-curves, S-curves. They plan an engineering profile. And then this is sent back to the subsurface community, and this is then an iterative back and forward, trying to plan the most effective well. What we're trying to do is break down this brick wall and bring all the data together into the same space. And as I mentioned, actually, the pilot studies we've carried out using this particular method save huge amounts of time. So in terms of bringing the target information, it means that all the property data, the geocellular data, any seismic, all the targets can be represented, but also in conjunction with the targets, any hazards, by the use of seismic, by the use of faults, any other information, that can all be incorporated in part of the well planning process. So this is really quite a new approach. I mean, to me, it makes a lot of sense to integrate this data, but in reality, it's a very rare occurrence for this actually to happen. So in terms of 3D visualization, this promotes geologic reservoir model-based well planning and directional drilling. The big important thing, having sort of worked with people using this method, is that whatever system is being employed, it has to be easy to use. And it's got to be a system that can be used in all domains. So there is no point in having a system that the G&G or the subsurface community can use and the drillers can't. So for a start, in general, it has to be in Windows and in Linux, and it's got to be something that different groups can all use effectively. There's no point in having a few expert users. The idea of a tool like this is that it should be used by all. I've just done some work for a group in BP, and the entire group of 24 were all trained in using this 4D visualization system. And the big advantage here is that everyone from the data manager to the reservoir engineers, to the geologists, to the geophysicists, everyone can pick up the data and has access to those files. And because everyone can use this, there's increased communication, faster, more efficient communication between the G&G, the reservoir engineers, the well planner, and the driller. So there's a lot of time saved, but there's a lot of better communication because all the data is being used and everybody has access to it. So what I want to do is sort of look at the traditional, well, in actual fact, when I started in the oil business, the drillers had no access even to anything in 3D. Everything was done in 2D, but it's very much, we have a slot at the top, 2 targets at the bottom, and this is very much what the drilling arena was like. There was no interaction with any other data. And in terms of what data can be brought in, there are some instances where I've seen with drilling where there may be some geologic information, but that's pretty much all that is available, all that is accessible. So what I want to show you now is the types of data that can actually be used by the drillers or in conjunction with the subsurface community. So I'm actually going to turn off these data files that we have available and start, in fact, with the slot, which we have up here, and 2 targets, which would be the sort of traditional starting point for drilling a well. Working with this co-visualized system gives access to the drillers of all the data types. So, for example, you can look at any offset wells that you have available. If you've got any well information, what we see here with this particular well suite, we're looking at lathe plots which are being created by a gamma ray, and we can actually color by any other property in the file. So we can color by V shale and look at different log information in relation to those well position points. We can also bring in our seismic amplitude. So the seismic can tell us an awful lot in terms of where targets are going to be, but also where potential hazards are also going to be. So all this information can come straight into the drilling domain. We can also bring in the geology and simulation data as well, and any well and temporal events. What makes this system, I think, particularly unique is, as well as being able to bring in data in a static sense, it also incorporates any temporal data and brings all this together. So you can also animate through time. So what we're looking at here is we have well status, so we're looking at when wells become producers, when they're drilled, when they become water injectors. We've got a simulation model, so we're looking at changes in the simulation model over time. If there's any 4D seismic, that can also be incorporated as well. So it's just allowing information from many different sources to all be incorporated as part of the drilling process. I'm just going to turn off a few of these data files. I'm going to turn off the geology and the seismic and just have a look at the simulation data here. And with the simulation data, again, you have the option to look at different parts of information. So, for example, you can specify ternary attributes and look at the change in gas, oil, water over time. This particular data set, this is actually a North Sea data set, and this is a real case scenario in terms of what I'm actually showing you here. For this particular well path that's being planned, we have our slot, we have our target points. The targets were based on mobile oil calculations. So if we move the mobile oil up to here, we can filter the mobile oil and just look at the high values. So what we're looking at with the mobile oil is the unswept area at a certain point in time. So that what these targets are doing is they are indicating where there is oil left in the reservoir and where the new well is going to target. And what we have here is a cross-section through the geocellular grid and also through the geologic modelling, showing the planned well path hitting the targets and how it looks, how the volumes look alongside that new well path. And what we can do is we can toggle between the geology and the simulation grid. Why this is a particular relevant data set is that wells were actually planned based on this information, and the targets were picked from the simulation grid based on the unswept oil. But when this was compared against the geologic model, this blue top horizon, if we go, I don't know if you can see on the bottom right-hand side, the horizon 13, which I'm just going to toggle on and off, is actually a shale. The simulation grid was targeting a sand which actually sits underneath the shale. And when these two data files were compared in their own space, it was shown that in fact the datums were mismatched, and they were down to a Kelly-Bushing. The Kelly-Bushing adjustment hadn't been made to the simulation model. And this is an instance where the well could well have been drilled on the basis of the information coming from the simulation grid, but without this cross-check against the data, which shows immediately that there is a mismatch, that wouldn't have been picked up until maybe it was too late. So what I want to do is, if we just have a quick look at the benefits of co-visualization, I'd like to just go through these quickly and then go into the well planning software and show how easy it is to amend a particular well path based on additional data that you have available. So 3D visualization, it brings together data from all parts of the decision-making team. It's easy to use, and the easier it is to use, the easier it is also to understand. But the important thing is what it promotes is increased communication between the subsurface team and the well planner and driller. It lets the data be viewed from both sides of the wall. In fact, it removes the brick wall in terms of collaboration and data sharing. It's fast and efficient. There's less time passing information back and forth, and decision making is more efficient and effective because all the data is being used together. So what I'd like to do now is look at some of the data in a bit more detail. So I'm going to use the well planning package that we've developed, Well Architect, which is, Well Architect is a typical well positioning and drilling tool. The interface, I think, is pretty standard with other packages. It's based on a database, and data is stored on either an area or an operator basis. So what we're going to do is look, and the tree structure, it has a traditional tree structure which goes down through a field, through the facilities, down to the individual well bores and planned well paths. So we're going to, in effect, plan a well based on the two target points that we've just seen. Using Well Architect, you set up a particular new well path, and you can use specify any additional wells that will be part of that particular field. By default, it will bring up your geologic model. What I'm actually going to do, because we've picked the target points based on our simulation grid, I'm going to turn off the geology and bring in the simulation data instead. And the access from Well Architect is exactly the same as it would be from CoVis as a standalone project. So all the data that's available in a CoVis project is also accessible from the drilling side. So it means that individual files can be picked as required. So what we're going to do is pick up the simulation grid we've already looked at. So I can pick up any combination of files at this point and compare them with the data. And we're all automatically looking at the mobile oil. Again, as I showed earlier, we can filter at any point. We can animate through and look at the changes in the mobile oil over time. What we're going to do is our starting point in terms of the well planning is we're going to set the time to the most recent date. And we can display this. We can put on the temporal date title. So in the simulation grid, the latest date we've got is 2004. So that's the time we're going to use. So what we're going to do is we're going to plan a well based on the two target points that we see here. The target points are stored in Well Architect in the actual database, but if we decide we want to make changes to any of the points, we can do that here. So for example, for the first, I'm just going to slice down one layer. So I'm going to the second K layer, which is where the target horizon is. So for example, if I want to move the first target, I can just turn on the 3D cursor and snap it to a different location. And now by editing, I can just move it to where that 3D cursor is. So it's very easy to move the target points or to use the 3D cursor to pick additional points on any of the other data types that you have available and incorporate those as part of the well planning process. So I'm just going to save the changes I've made. So that's available. And now if we go back to the well planning side, what I'm going to do is build a well through those target points. I'm not a driller, so fortunately we have an expert mode and a beginner's mode, and I'm going to use the beginner's mode. There's less data that needs to be input. So the slot is at the top of the other offset wells. I can just zoom out a little bit. And I'm going to start by, I can now build my well plan based on a set of engineering profiles. So I'm going to start with a tangent and give a value of 1,000 meters. So we'll just have a look at this so I can just show you. So we can see the blue line at the top, which represents the starting point of this particular well path. Apologies, I've got very little room for my mouse here, so it's slightly cramped at this side. So the next thing I'm going to use, I'm going to create an S-curve, a 3D profile S-curve, and because I've selected to use the non-expert mode, the blue boxes need to be completed, only the blue boxes. If you're in expert mode, you can complete all the inclinations and azimuth and put in every part of the actual profile that you're creating. So for an S-curve, it's 2 arcs and a tangent. And I'm going to select my first target. I have 2 associated targets with this particular well path. And I'm going to pick the first one and use the little bullseye here to target, to pick that value. Because I've created an S-curve, I also need to input the inclination and azimuth to that point. Because to build the profile, the program needs to know what angle and azimuth I'm going to hit that point. The other option is to define what point is beyond the next point beyond that. So I'm going to use for the last point, I'm going to use my second target. The only information now missing is the dogleg severity, which is in degrees every 30 meters. So I'm just going to put a dogleg severity of 5 in both, and that will now complete the well path. So building a well path is incredibly quick and straightforward, and we can see that we now have that well path completed. When we looked at the geology earlier, you could see straight away that the well path was actually in the wrong place. And the important thing, what we realized was that the Kelly bushing, we could go back and correct the simulation grid, or we could actually check against the 2 data sets and see what discrepancy there is. So what I'm going to do is bring in the turn on the geologic model and turn off the simulation grid, because we've in effect honored the points we need from the simulation grid. And with the geology, what I'm going to do is turn off the transparency and create a new profile along that new well path. So from the slice menu, I can create a path slice using the new well path that we've just built. So if we zoom into the data set here, I'm just going to turn off the top fill zone. And the blue top zone here represents the shale. So we've got our 2 target points sitting in the shale, and we want it to be below, actually, to hit the sand. So to do this, I'm just going to turn off the target points initially. And I want to be able to sort of see what discrepancy there is between the well path that I've created and the top of the sand unit, which is where we're targeting. So there is a quick measurement tool here. So if I use the measurement tool, I can see it's probably about, if you look at the measurement below, it's between 15 and 20 meters higher than it should be, which is approximately what the Kelly bushing is. So if I go back to my well plan, I can adjust the target point which I had, which is 2035, and instead of 2035, I'm just going to add 15 meters to it and make it 2050. And that will be immediately updated on the trajectory up here. So this is why having the additional information means that you can make small adjustments, still maintain the integrity of a drillable path, but correct it to the other information that you have available. For the end of the path, again, I could just adjust the point by 15 meters, or I can also use the 3D cursor to define a particular point. So if I choose a point here, and instead of using the target, I can pick that last TVD and just use the 3D cursor instead. And that will bring the 3D cursor, it will bring the trajectory down to where the 3D cursor is. So now what we have is a profile that honors the location of the unswept oil and also honors the integrity of the geology. So this is just shows an example of just two types of data that can be used, but any information that you have available from your subsurface community can be incorporated in the same way. So speed-wise, this is a huge improvement on any methods that I've seen so far. So the final slide, just a quick conclusion. The benefits. Using 3D and more than 3D, using 4D visualization, if you can see your information, you can understand it. And this isn't just in terms of one particular discipline, this is cross-discipline. What the advantage of having all the data stored in a co-visualization system is that all the members of a team don't have to learn each individual software package. If you're a reservoir engineer, you can pick up a seismic volume without having to go and learn the intricacies of size works. If you're a geophysicist, you can actually access the well planning software. You can pick up the simulation grids. So it gives the end results of all the different software packages to the entire community. So it's a huge benefit in terms of understanding each other's domain. The important thing for this particular system is that it is very easy to use. So it can be used from technologists up to experts. It's something that can be picked up and used rarely, or it can be used on a day-to-day basis. And because it's easy, what we've found is that a lot of users, particularly in the reservoir engineering world, will use it in preference to their own systems because they can load data very quickly and they can see what they want from it. And it may not even be in conjunction with other data sets. What it certainly does lead to is increased communication. What I've found is for people who are using systems like this is it's the starting point for any team meeting because it's something that everybody can understand, everybody can actually identify with. And the more people who can see all the data, the greater the understanding. And it's fast and efficient. So the bottom line is that it saves a lot of time and ultimately a lot of money. I think the big problem we have in the oil and gas business, as we've discussed this morning, is that because we are a fairly wealthy business, there hasn't always been the incentive to do things the most efficient way. We've got away with doing things the way we always have. And because people tend to be busy, there is a reluctance to try new technology, to try new software, to try new solutions, when in fact there'd be a huge benefit by taking on those new solutions. Thank you very much for your time.
Got time for any questions from the floor here? Just one comment for you, Jean. One of the key issues I felt in geologists or geoscientists talking to engineers was uncertainty. the engineers want an answer to 2 decimal places, and the geologist given one, and even though they know it's going to be this wide. As soon as you put that well in that surface, engineers will expect that to be certain, whereas an error bar around those certain... How do you communicate that sort of error bars around those surfaces and do predictions?
Well, I mean, there's there's sort of no easy way of doing it apart from doing multiple scenarios. So obviously, if you're looking at certain scenarios, you will look at base case, you will look at best and worst case. But I think anything is better than nothing. And I think for drillers to go back to the 3 points in space scenario, having the drillers I'm working with actually are really keen to have the seismic, are really keen to have any information, because they feel that enhances what they can do. It gives, they feel as well that it gives them more control in terms of how they plan the wells, whereas just planning a trajectory and sending it back, they haven't got a lot of control over what's happening. They can't give their input.
Okay, good. Thank you very much indeed, Jane.